So yeah, I mean, F0 estimation is different from transcription, where F0 just grab whether there's something happening. So that's what we call frame level annotation, where you just annotate whether it's 0 or 1. But you think about onset and how do you group those ones into like a note. And finally, if you want to make it into SATB different string. So there's a bunch of additional steps towards final goal of music transcription. Let alone you want to make it into sheet music where you also have to quantize the duration into musically meaningful duration, like quarter notes, half notes, rather than it's just like milliseconds. There's some commercial ones, even though most of them are still far from good. So this is like an ongoing work where progress is steady, but we are still far away from anything that's very robust to all different instruments and polyphonic scores basically. There's also multi-track transcription, which is very challenging but fun at the same time, where you basically want to do transcription for multiple instruments at the same time. Questions on transcription? Cool. Um, yeah, we also talk about key detection, chord detection. We didn't technically talk about it, but you can experience it in voices. And more interesting or more useful is like beat and downbeat estimation, where you basically want to annotate where those peaks are. So typically that was done by doing beat estimation. So this model basically scans through the audio and look for plausible peaks and try to annotate where there's a peaks at that particular time point. So you can think about this as, sort of like binary classification along all the candidate timestamps. And you have to do some filtering. You have to do some, peak selection so that you get all those, beat and downbeat locations. So this could be useful, in like sampling or, if you want to stretch or, dynamically change the speed of the music, especially in sampling or, DJing, if you want to scratch it kind of, then these would be useful. Or you want to do a mashup between two songs, then you potentially want to, shift from one BPM to another BPM smoothly. Then in the boundary, then you want to do some, beat stretching. We also talk about structure analysis. This is much trickier than people thought. You can do it on symbolic. You can also do it on audio directly. But this is one of the very interesting things that we sort of want to we talk about. This is self-similarity metrics. So you can visualize some of the repetitive structure, repetition basically. So this is one of the way that you can extract the boundaries. So you basically scan through these things that detect whether there's like a boundary, like black at the red region and then white in the blue region. So if you just scan through the diagonal, then you can get this novelty curve. So whenever there's like a big activation, meaning that there's some border between the sections. And we talk about OMR. Basically, this is very challenging to do it. You have to do a bunch of things to, accommodate all the different OMR scenarios, which are more interesting than, if it's just like a, more than, sheet music. That's much easier than, these handwritten or, historical scans of those artifacts. The development pipeline look like this, but basically analyze this layout, extract all the staff, and then you do, transcription on each of the staff, and then you just concatenate them back. So you can do sort of like musical object recognition, but the challenging part is not only, just recognizing which are the objects, but how do you convect them and turn them back to the sheet music. Cool. Any questions on the analyze part? Cool. So today we will talk about classification, but more specifically, we will also talk about PA4, one of the only model that we will train in this class. Um, Cool. I think I've not yet finalized the question yet, but it will be up soon. Um, cool. But homework 3 is up there, but that's for generation. And PA3 will be due on Wednesday. Cool. Um, any questions so far on anything? Oh, good. Okay, cool. Yeah, so music classification, it's kind of interesting to ask what does music classification mean. But generally, you could do all sort of like classification tasks, and there's so many different applications. And even, nowadays in generative AI era, there's still usage of new music classification models. To think about genre classification, you just want to classify it a song into, pop rock, R&B, jazz, hip hop, classical, simple genre definition. But also you could think about mood classification. This could be, useful, if you want a Spotify, playlist, that's like melancholy playlist, or, studying, playlist and, happy, sad, calm, aggressive, cheerful, exciting, things like that. You could also do instrument recognition. This is one of the things we will do in our PA, where you will just look at like audio and try to detect what that instrument is. Composer identification, this is very interesting because this has some implication on, musicology and, music theory to look into what are the difference between composers. And, it also have, potential application into linking the evolution between different styles. That's very interesting, rather than just identifying the composer, because most of the time you will have like metadata for those. Key detection, we talked about it. Core estimation, those are not song level, but more um, you know fine grain annotation. Music tagging, this will cover everything at both, basically. You could be instrument, composer, mood, and genre. We would talk about it. Basically, multi-label classification. So there's so many application for these models. Think about recommendation on, Spotify, YouTube Music, Amazon Music, all sort of different music streaming platforms. So this is um, one of the most needed algorithm in the industry. Curation, so think about like RD for not RD, A&R in the music label company. They want to see, or you're a streaming company, you want to see what are the type of music that are currently underrepresented in your database or your pool of available content. Playlist generation, there's so many AI playlist generation models nowadays. And recently, Spotify just announced that now ChatGPT, you can actually generate a playlist, just like prompting ChatGPT, and it will just link, like embed like Spotify interface. And then if you click it, it will bring you directly to Spotify app. So there's a lot of things going on, especially leveraging LLMs for playlist generation so that you can be more personalized. Listening behavior analysis. This is also very interesting if you have looked at some of the Spotify and YouTube Music's, example at the year end, it will sort of like look at what's your listening behavior. Then this could be, doing recommendation much more precisely so that the platform can knows what you're most interested in. Also musicology research, that's also sometimes under being overlooked somehow. So there's also implication about how music evolve, how different genre relate to one another. So all sort of musicology research. Also regional styles. So one of the most iconic way is to look into music classification core recommendation. Well, these are the most used streaming platforms. So this is a very interesting result. So Spotify and Amazon Music is actually surprisingly high subscription rate. So this is not like how many users there, but more like how many paid users on all these platforms. So you can see that actually Amazon Music has more paid users than Apple Music and YouTube Music. But this is based on only 2,000, survey attendees. But it's interesting to see that both in UK and United States, Spotify and Amazon, YouTube, Apple Music and YouTube Music are dominant in. Um, so what can we do about recommendation? So, easy stuff, what to play next. So most of the time you just click on one song and that song will be like 3 to 5 minutes or, classical music, 20 minutes, unless you are doing, soundtrack, then it will be much longer. But otherwise you want to know what to play next. Then in this case, knowing the genre will be very useful to see, how can you recommend the user about what to play next, basically. But also, think about it, extend it a bit further, then it become playlist generation. This is one of the hottest topic nowadays. And, combining LLM's ability in understanding human prompts, like what exactly the user is trying to get from the prompt. And at the same time, you want to generate a playlist that accommodate what user is looking for. So, classification would be sort of like the first thing you have to do so that you know what are the tags and what are the genres. You can also do annotation manually, but sometimes if you want to be more personalized, more targeted, fine-grained annotation, then sometimes these music classification models would be helpful. So, similar genre could be helpful to put into the same playlist. But, more recently, I think the one of the most sort of like the front line of music AI research for, these streaming companies about AI playlists. So this is like Spotify's sort of like solution. Later we will see another version for GPT, but this one is like baked into Spotify's app where you can basically just click this AI playlist and then you can try some prompt. So think about, generate a playlist to help me focus while I'm reading something or I'm trying to study. Then it will sort of try to use some LLM to interpret what you are looking for and then generate a playlist for that. So this was like back in February, no, April 2024. So, it's just 1.5 year ago. And YouTube last year also have a similar feature where you can ask music, basically the same idea. You can ask something. So it's something like Gemini for Google Verse. But once you ask it, it will generate a list of songs that fit your particular prompt. But more interestingly, it's just like last week actually, October 6th, not last week, 2 weeks ago, Spotify just announced this personalized picks in ChatGPT. So now in ChatGPT, you can actually just talk with ChatGPT and at some point just like, can we have a playlist in Spotify on blah, blah, blah. And it would basically just do it. So this is like leveraging like OpenAI's like recently launched like B2B service where you can bake your product into ChatGPT. And so I think that's one of the most powerful or, more easily commercializable application of these, chatbot ChatGPT, applications, because basically that's how they can earn money from. To think about Google search, where you go to Google search to search about something. So, by getting the revenue from the ad in Google search, Google get to earn something. So now if ChatGPT becoming the next generation, entry point of the digital world, then who can control these and who can be embedded into these service, then they will have a much higher visibility so that they can, attract their audience. So not sure what's going on in the future, but, at least now there's like interesting application popping up. And I guess, now Spotify with ChatGPT, but soon it will be more, much more competitive in the business round. Have you tried any of these models? The S. Oh yeah, cool. What's the streaming platform you're using? Spotify. Okay. I'm using YouTube Music. I somehow stuck. with YouTube Music because the algorithm is just, I mean, it's just like personalized to me. And whenever I use Spotify, I feel like I have to train it for a month. And then you're just stuck, kind of. Yeah, I've tried Spotify and I also tried like Amazon Music, but I mean, I couldn't wait for a month to just have it learn.
YouTube is much better. So they don't shuffle your songs.
You mean Spotify? Yeah.
You still get ads.
Yeah. Cool. Oh, and I also use YouTube Premium so that I get both. Yeah. Otherwise, I mean, in class, whenever I click the YouTube link, then there will be like 10-second ads. Yeah. Yeah. Cool. But there's also like interesting things. Sometimes I would just look at these and like, oh, interesting. That's how I have listened to the music. So YouTube have like this music cap recap every year. I think this was like a while ago. I don't know. 2024. And this one is like 2023. Spotify is like listening personality. So I don't know, kind of interesting to see what kind of behavior you're doing. So underlying this is also could be like sort of like a marketing strategy for these streaming platform, even though it's a little bit different from shopping experience in store shopping experience. But you could think about it's just a different way of doing recommendation and marketing. Cool. So that's sort of the landscape of why we are doing all sort of like music classification. But the rest I would just talk about, the way how we frame it into machine learning framework. So likely would be kind of simple. So we would just fast forward it, I hope. So, type of classification task, like basically binary classification, multi-class classification, multi-label classification. These are the three, most common types of things. Binary classification, kind of straightforward, where you just have an audio, go through some neural network, and basically want to see whether it's classical music or not. So things like that, asking a yes/no question. So how do we do it? Usually we will go through this the sigmoid function thing we talk about. So this is called logistic regression. Basically, you will generate some number, and whatever the number is, you will pass it through a sigmoid function. And this sigmoid function will turn it into something between 0 and 1. So you can sort of like think about it as sort of like a probability, kind of like how likely or how confident it is about this song to be classical. Even though that's not the exact way to interpret it, but oftentimes, you know, the underlying way of understanding these, like the intuition is sort of like a probability or confidence like measure of the outputs. To think about, there could be other songs, then all these different songs would have, different value about whether it's classical. And these numbers in between, it could be anything from negative infinite to positive infinite. So all these number, if it's negative, then it's more likely to be no, so under 0.5. If it's positive, then it's above 0.5, then it's more likely to be classical. So usually you will set the threshold, usually 0.5, but sometimes if there's like imbalanced data set, then you want to try to find a better threshold. So in this case, if we set like 0.5 as the threshold, then in this case, you could just do this binary classification. Then multi-class classification. So this will be our PA4, basically. We will just go through these sound. There's no sound. As usual. Let me see. Hmm. Oh, actually. Oh, I did connect. Well, let me try again. Yeah, that's the sound. So it's like a full second. what it should be. Like a 4 second, like single shot instrument sound from this data set is like a commercial, sort of like commercial software. So, think about in Logic Pro or whatever DAW, you have like that instrument bank and you just press each note for, in this case, they press it for 3 seconds and then like let it off. So they will have some ADSR, but in this case, this is like organ. So the ADSR will be, you would just hold, and at this point, it will just decay rapidly. And so in this case, we are rather, doing binary classification. Now we are basically trying to predict which one of these, potential instrument would be the case. And so in this data set, there are 11 different instruments. So you could sort of like see how some of those could be a little bit tricky to define. So think about keyboard and organ, keyboard and string, and, synth, like it's potentially quite sort of, quite confusing in some sense because, technically instrument, especially electronic instrument, is a little bit tricky to define. But this is basically, the idea. The data set come with, a bunch of different, 4 second, samples of different instrument, and you want to classify what that instrument is. So in this case, now we are not doing, single class classification. Now we are doing multi-class classification. So essentially what we want to do is sort of like a distribution of like how likely each of these things would be. And in this case is the flute case. So that's not the sound that you just listened to, but imagine we have a flute sound. Then in this case, we will get, like a very high activation on the flute. So that's essentially how you can do multi-class classification. You could potentially just train this model to output some of these things. So this could be used in the softmax thing we talk about. So it would turn the output values into something that's sum to one, so that you sort of get like a probability-ish things. And in this case, it will have a very strong activation at the flute category. So you will see it in PA4. Basically, at the end, we will go through like a softmax, and everything will be, sort of like limited into 0 to 1 and sum to 1. So you can get sort of like a probability or confidence like measure of the output. Cool. I assume these are not too tricky. So the most tricky one is about multi-label classification. And this is actually what, most case we are talking about in music recommendation is about, is that, music is a little bit tricky to define the genre. So oftentimes you will have, multiple, tags for each single song. Like even like just looking at the album, it's a little bit tricky to show you which song is that. But, looking at the album or, the artist, you could sort of guess what that genre is. So it could be, soul plus R&B plus pop. It's a little bit tricky to define, soundtrack, classical, but, soundtrack could also be electronic. Soundtrack could also be, alternative rock and roll. So there is a bunch of different, overlapping genre, or, alternative is sort of like a subgenre of rock. But if you just do rock, it could be too, broad. Then you want to make it more fine-grained. So this is sort of the idea we are looking into. So potentially we are not just predicting whether it's like one single class or not. We want to tag it basically. So the idea is now we are not generating one single label, but now we are generating a set of labels on top of these songs. So there are two ways to do it. One of the easier way is to just look at, it's like a binary classification. We just look into this, the sound. Is it classical? Is it soul? Is pop? Is rock? Is R&B? So think about it as just basically doing a bunch of binary classification on each of these. And, potentially in this case, if it's like a, soul plus R&B album or song, then it would be, in this case. So this is one of the more, the easier way of looking into it. So this has some, practical challenge in real life, is that, it's very hard to adjust the threshold, because the threshold will sort of like correlate to the frequency of these, instrument tag. So oftentimes you are, think about is R&B, this binary classification, 90% of time it's not R&B, because there are so many genres. So unless you are like an R&B only label company, otherwise, each of these genre would be only 10% or even like less than 1% chance to get it. So it's much harder to train these kind of model where 99% time it's a no and 1% time it's a yes. So it's a little bit tricky to, tune these model, but, think about it this way is that, well, we could technically just do a bunch of binary classification to do it. There's also another way to do it. If your class, potential instrument, I mean, not instrument, in this case, genre case is not so tricky, then you can actually just do it as a power set. So this is called label power set. Basically, think about if it is just three, four different label, pop, R&B, soul, and classical, then you could potentially go through all the different combination. In this case, there would be 2 to the 4th minus 1, so 15 case. You could also add like a empty set, then it will be 2 to the 4, 16 possible combinations. But in this case, now it becomes a multi-class classification rather than doing binary classification each. So in this case, it will be, well, looking at all these different possibility, which will be the one that both most, representative for this song. So in this case, then pop, R&B, soul without classical is the ground truth. But you can also think about this could basically explode if you have too many genres. But in the case where, think about, a much more constrained label set, then label power set could also be very helpful so that you could potentially alleviate the imbalance problem. Question on this? Like the two ways to do it?
Could you also accept the label as like 23 pop? Like,
Oh, that would be cool. And I believe people do that, like make it more like a confidence level. But to break it into, something sum to one, that would be a lot trickier. Yeah. Because oftentimes, these model doesn't actually work like that. It's more like these models are basically doing classification. And by classification, it's like try their best to see which one is the best rather than decompose them into, multiple components.
each label, then you would run into the same problem as like doing a bunch of binary classifications, but you might just get a lot of like groups.
Yeah. But you could also think about, if like it's pop, then potentially 90% of your song will be it's pop. Then potentially you want to do, J-pop, even like language or, other, regional pop music style. So yeah, so and it's rock, it could be 50% of that. Usually all the data said there will be like 50% ish rock songs. Everything just like sort of market. If you look at the drum patterns, some usually you could just, it's like rock and roll drum groove. But if you look into the subgenre, alternative, metal, aggressive, so there's so many different rock subgenres. Yeah. And there's also a branch of classification is about hierarchical classification. So potentially you are not doing, just like flattened classification. You are doing hierarchical, sort of like a taxonomy of the genre. Then in that case, it's like, well, if you get an alternative, but you don't get a rock, like a meta genre, then it will be kind of weird, right? So in that taxonomy case, it's like, well, you are doing multiple classification at the same time. But at the same time, meanwhile, you are also trying to build that tree so that it have like genre, subgenre, case of like a tree of genre.
So like that.
Yeah. But you can think about like it could potentially help like how you do classification. It's like knowing that, this song is alternative with like 90% accuracy, then it's highly likely to be a rock song. So there's like implication between the correlation between these labels. And think about jazz and blue. There's like correlation between these labels. That's why, classification is not always the best way to look into these, models because potentially are like overlapping and correlation between these labels. So whenever there's like correlation between labels, it's the most tricky one in machine learning. Um, but in practice, if you want to do tagging, then basically it's like try to be as accurate as possible. And usually we evaluate those models using overlap between the label set output with your prediction, how many, tags you actually get it right. Yeah. So, we sort of like simplified it a little bit. But there is a tons of, extensions on, hierarchical classification, but also, building that taxonomy and, doing more fine-grained, genre classification. Um, yeah, and we are talking about genre here, but think about emotion, think about other like functional or purpose, functional type of music. Like this is more like a background music, or that is more for activity for festival. All sort of classification tags could be potentially useful. And usually when we think about the input features in homework, I mean, in the PA, we will be looking into spectrograms, but now some of the models also just look at, raw waveforms. Sometimes there are additional information in the waveforms that could be very helpful. But spectrogram will be much more efficient, of course. There's also handcrafted features or, using features provided in metadata. Sometimes, additional information about the genre could tell you something about the composer, and vice versa. So there's a bunch of different things that you can do. So some of the most common features, loudness, pitch, and timbre, these are kind of simple inputs. Beat, tempo, time signature, these are, content-based classification where you can grab additional inputs using all the, MIR feature extractor we talked about in the last few lectures. You could also do key scale chords for tonal things and instrumentation, expression, structures. Also the things, these MIR features could be helpful. And these are some of the common data sets. And it's still ongoing. And one of the main challenge of MIR research is that these data sets are usually not possible to share around. So one of the most iconic one is the million song data set. This is like 1 million songs with all the features sort of extracted. You can share the features, but you cannot share the original audio. But there's actually some way you can go to 7Digital. That's like a platform that has like 30-second preview of almost all these 1 million songs, I think 70% at least. So you can actually get, and it's also marked with so many tags. So this has been like driving the MIR research community for a while, but it's very tricky to access. And usually oftentimes it's just like groups sharing across groups. But there are also, GTZUM is one of the first data set look into genre classification. It's just only 1,000. So now you think about it, it's like crazy small, 10 genres, but that's where it all started. And there's a bunch more new ones, MTG, Jamendo. Jamendo is like the CC license website where people upload, sort of like a community-driven website. And Free Music Archive is like another website people can submit, free. It's part of like, I don't think it's part of Free Sound, but it's sort of like similar idea where you can submit, CC license or public domain recordings onto those. There's also AudioSet, which is the huge one that with Google. So there's sort of like all YouTube URLs, but this is a bit tricky because sometimes like low quality audio because those could be potentially just YouTube videos of someone's recording rather than the original production level version. And since it's not essentially like a full song, but it's like just 4-second one-shot instrument sounds as we will see in PA4. So we will talk about it later. But also another challenge in classification is about evaluation metrics. Um, so I guess there's no one thing about machine learning is that people oftentimes just look into like how are you evaluating these models, what's your accuracy. But I guess one of the key about understanding machine learning is that there's never one single evaluation metrics that you care only about, or there's just not one fit all evaluation metrics. The goal of evaluation metrics, you oftentimes want to have a suite of metrics so that it can capture what you care the most. So, it depends on the actual use case, and it's always better to use several, a suite of evaluation metrics to obtain a holistic view of your model's performance. Um, so in the next few slides, we will just jump into like a simple binary classification to sort of like show you why there are so many nuance on evaluation metrics, and choosing the wrong evaluation metrics sometimes will lead to, catastrophic results, or, just a poor performance for your model in practice. So think about this like perfect example of like binary classification. Half of them are positive, half of them are negative. And, you know, um, imagine, this is your classification model that you predict everything at the left as positive, everything at the right as negative. Then, I actually forgot what exactly I'm drawing here. I think that's the decision boundary. So yeah, you're predicting everything with blue background as positive, everything with orange background as negative, and you have these ground truth labels. So in this case, you can see that there are something getting wrong. In this case, you get wrong with some of those. So we can usually look into these things as true positives, meaning that you are doing correctly. So, the you predict it, the ground truth is like a true, like a positive sample, and then you label it as positive. And then similarly, you have like true negatives. These are negative samples, and then you mark it as negatives. So again, this is like binary classification. So you are just doing, true and false, basically. So more interesting, false negatives, where, um, it should be negative, but somehow you predict it as a positive. And in this case, it's like it should be a positive, but somehow you predict it as negative in this case. So, this is the decision boundary. So everything in the right is negative. You predict as negative, but, once you reveal their colors, there's actually, positive ones. So those are false positives. So one of the, iconic things that people usually talk about is this accuracy thing. So accuracy is basically just looking into everything you did, you've done correctly. So and put it in the um, the numerator. Everything on top. So those are things that you do correctly, and everything at the bottom. So that's everything, the whole data set basically. So in this case, you basically do 0.82, 82% accuracy, because you've did it wrong for these four case. So these four are included in the denominator, but not in the numerator in this case. So this is basically like the accuracy thing that we talk about. So this is fine, especially in this case where it's like very balanced. And we will see later, when you have an imbalanced data set, then accuracy become much more distorted. But one thing I want to talk about, and that's the reason why I haven't done it, haven't finalized PA4 yet, because we will also look into some of these confusion metrics. So, basically, this is the confusion metrics that you can look into. Oftentimes, very useful to look into what's going wrong with your models. So basically, you put prediction at the x-axis or ground truth at the y-axis. Sometimes you can swap it. But basically, if the ground truth is positive and you predict it as positive, so this is like true positive, so you did it correctly. And if prediction is negative and the ground truth is also negative, then this is like true negative, so you did it correctly. So these are the two, type 1 and type 2 errors. I always forgot which one is type 1, type 2 errors. But anyway, one of those will be false negatives. So this will be things that, the ground truth is positive, but somehow you predict it as negative. And then, if the ground truth is negative, but somehow you predict as positive, those will be false positives. So I think I technically get it wrong in the previous slide. But anyway, that's the definition. So you can think about, if you have a cat and you predict as a cat, then it will be a true positive. But if it's a cat, but you predict as not a cat, that it will be false negative. And the same thing for the dog cat's case. Whereas a dog is not a cat and you predict it as not a cat, then it's true negatives. But if it's a dog and you predict as a cat, then it will be false positive because you mistakenly assuming that the dog is a cat. So that's a false positive. So this is like the confusion matrix. Whenever you look at like the percentage between these four different categories, you can sort of like diagnose into your model. And so that's what we would be doing into, these imbalanced data set. So one of the key thing about why some of these evaluation metrics can be very distorted, especially on imbalanced data set. So now, usually we will think about some of the most impactful application domain. So think about you are doing, disease diagnosis, and think about a disease with just 1% prevalence, for example. Then, what if we just simply say negative to all diagnosis? So you are just like basically, well, I don't care. Everything is negative. It's just 1%. I don't care. Everything will be negative. Don't ask me. I won't do any analysis. I will just say it's negative. So in this case, if you look at the, think about like if you do 100 diagnosis, then 99% of time you would do it correctly because you will be 99 cases of true negatives because those are negative case and you predict as negative. But there will be one of that false negatives where it's actually a positive case, but you somehow because your classifier is just like say negative to all diagnosis. So in this case, you actually get an accuracy of like 99%. So this is like one of the iconic case where, accuracy doesn't show you the exact idea. So, in music, it's like, well, think about, I don't know, think about like a pop song, um, you know, pop song classifier, then, pop song, 90% of them are pop song, or think about a very specific genre. I don't know. Can we think about a very specific genre? And the metal is not that specific, but I guess it's like less than 1%, most likely. But you could even think about, I don't know, the very, very niche, very sub-genre of a specific classifier that you want to train. Then in that case, it could be less than 1% prevalence. So in that case, if you think about accuracy, then you are basically just looking at those like 99% of net negative case. And, it's like if you just do this baseline model that just say, no, it's not, a metal song, then it will be 99% accuracy. So to fix this, there is actually some other evaluation metrics. So usually, oftentimes, we will look into other metrics to sort of like look into these. So the first one is like precision. So basically, precision is TP over TP plus FP. Oftentimes, very tricky to see what those are, but basically, from all the things that you predict as a positive, what are the case those are actually true positive. So in other words, in this case, it's like 75%, but in other words, it's like how often predictions for the positive are correct. So that's usually, think about, how precise your model is. Once your model predicts something is positive, how likely it is actually positive. So in this case, you don't look into anything that you predict as negative. So in this case, if you think about the metal classifier things, this doesn't work if you just classify everything as not metal song. And if you want to nail it, then precision will be very tricky to do it because there's just 1% of metal songs music in this data set. And how do you even get those correctly? So this is precision, how often predictions for the positive are correct. And the other things we talk about a lot in like recommendation system, as we will see, is about recall. So recall is a little bit different from what we talk about just for precision. Recall is TP over TP plus FN. So visually is basically, everything in the ground truths. So I've talk about it around it. So the background colors are the ground truths and the colors are of the dots are your prediction. So everything that is the ground truth is like positive. How many of those? What is not showing? How well the model finds a positive instance in the data set, basically. So in this case, there are, 10 of these are actually positive samples, but you only grab 9 of those. So this is like especially used for in, music, recommendation system rather than just music or retrieval system. It's like, well, I'm trying to grab a bunch of, songs that potentially be interesting by the user, how likely you grab those positive instance from the data set. So precision, again, how often predictions for the positive are correct, and recall would be how well the model finds a positive instance in the data set. So these are false alarms. So precision look into the false alarms, and recall look into the miss detection. So when should we care about precision and recall? So in this case, think about rare cancer detection. We want to aim for high precision or high recall.
Be most interested.
Like which would be more important in this case? Um, it's a little bit tricky without looking into what precision and recall is. If you want to ask me, and I don't really know, I would just do it myself. So think about, rare cancer detection basically is that, well, we do have very rare case of positive. So in this case, there's just like very few of those. So most likely everything is negative for their ground truth. So in this case, you have false negatives and false positive. These are things that you care about, right? So either false alarms versus misdetection, which one is much trickier in rare cancer detection?
Definitely be more interested in these detections.
Yeah, exactly. So, false alarm is fine. It's like, well, I did additional, diagnosis. And in the end, if not, that is, there's like mental, damage likely. But it's better than you miss the detection. So in this case, false negatives, those are missed detection would be very bad, but false positive, those false alarms, it's likely fine. You could just do additional diagnosis, and hopefully it's just like some mental pressure over time, but at the end you still likely not miss a lot of detection. So in this case, high recall would be much more important in this case. But now think about, a recommendation system where you want to look into a huge database. There are so many examples that you potentially can get, and it's very hard to cover all of those. So now again, think about, do we care more about false alarms or misrecommendation? So in this case, false alarms would be much more trickier than misrecommendation because, there's, thousands of potential songs that could be interesting in for this user. And it's fine if you miss one of them. And if you're thinking about like a playlist or next song generation, you're basically just grabbing one. You don't really care whether you cover the whole data set of all possible, think about want to find Taylor Swift songs. There are like thousands of Taylor Swift songs. Then how would you get it? How can you cover it all? But more important is like you don't want to get those false alarms where you grab something that's apparently not Taylor Swift songs. So in this case, user recommendation, if you think about next song prediction or, just like one by one recommendation or retrieval case where, it's very dynamic, where user will just look into it. If it's not relevant, then you just basically ruin it. But this is like more from the retrieval side. Then in this case, people focus a lot on the precision. But also, in the recommendation system, there's also other cases where you care about recall. So think about playlist generation. Then now you are grabbing all the songs from Taylor Swift. Then you want to cover all the songs from Taylor Swift. Then potentially, grabbing some wrongly classified or Taylor Swift like playlists. Then you want to grab a bunch of other songs. So it could be more exploratory behavior, then you can potentially want to care more about recall. So it's always not like a simple questions about which one is more important. It depends a lot on your use case. In this case, if you're thinking about just next song prediction, then likely if it's the wrong songs that you are grabbing, then the user will likely just close the app or just use another platform. So high precision ensures that the model won't recommend irrelevant items. I mean, the rest is just about F1 score. Basically, you want to consider both like precision and recall at the same time. So it's actually a lot of like music search, retrieval, and recommendation. You will see on the paper, they basically report these F1 score. But it's sort of like complex in the form, but it's basically the harmonic average between these precision and recall. And this is basically its formulation. So it's the inverse of precision, inverse of recall, and then use 2 to, divide over that. And this is actually the definition of F1 score, but basically it's the harmonic average between precision and recall. There's a reason why you are using harmonic average rather than typical average. But anyway, there's some math behind this. But this is usually how people do it to sort of like get a sense with both precision and recall at the same time. And this will be different from accuracy because accuracy is like, you just look at those, diagonal where you do it correctly on the prediction. But F1 will look into, precision and recall where, precision has its own meaning, recall has its own meaning. And oftentimes you want to look at precision, look at recall, look at accuracy, look at F1 score, look at all sort of things to get a more holistic understanding of your model. Um, Cool. So, as we talk about confusion metrics, it's another way to look into how your model is working. So this is the reason why I'm still finalizing the PA, but basically, hopefully, I will add this question to PA where you will draw this, multi-class classification, on the confusion matrix, the confusion matrix for your model. So, at the axis, it will be prediction, y-axis will be ground truth. So it's always interesting to look at these because if you look at the horizontal things, you can see that here at the top, there's like bass sounds got classified as keyboard sounds. So this kind of makes sense because some of the, bassy part of the keyboard will sound a little bit like bass. It's like a little bit tricky to look at it, but it won't be classified as string or, something else. But also you look at guitar. Guitar is a little bit tricky. So guitar as bass, bass is technical bass guitar. So guitar sounds, if it's like low pitch, then potentially could get classified as bass or keyboards. So, looking at the confusion matrix, sometimes you get a sense whether your model is doing something reasonable. And also sometimes if you look at, chord, classification, you see that, C major and C major 7, there's potentially overlap, then, your model is likely doing something right. And if you do like C major over something, I don't know, something that's not likely as any, overlapping nodes as, D major, then likely your model is not doing the right thing that you want it to be doing. So, confusion metric is a way to look into what's going on with your model. Is your model's output actually sort of like an indirect way to prop into your model to see whether it's doing something reasonable. And organ sounds got classified as vocals. This is interesting because if you look at the things, flute and organ and vocal is likely those are more wind instrument like, and organ and vocal in this case the vocal is like synthesized, not real vocal. So these are sort of like R sounds, and it could sound more like organ. Um, Anyway, if you're interested, there's actually a tutorial on music classification. There's a lot of things, beyond supervised learning. That's essentially the title of this tutorial, towards real world applications. So, so these are folks. Mins is now at at Suno, but he was once at Spotify, and Kyung Yu also work at some music tech company. So they have like real life, industrial experience on how, these things, music classification actually works in industry case. There's also like open source music classification models. These are two of the iconic one, but there's a bunch others. Um, I think that's all we can get today. Homework 3, not homework 3 actually, is PA4, music note classification using CNNs. I will send the emails as soon as possible, likely tomorrow. But basically what we will do is just train a CNN, convolutional neural network that can classify audio files into their instrument families. So we've seen something today. The input will be 64 by 64 male spectrograms. I already done this pre-processing. So male spectrogram and spectrogram, the difference is that you actually do some frequency axis remapping so that it actually highlight more human range of frequency, human ear frequency range, so that it will amplify those range. And if the sound is like too low frequency, too high frequency, you actually get lower resolution. That's basically what male spectrogram is doing. So this is like male spectrogram. If you do like traditional spectrogram, everything will be sort of like in the lower frequency part, and you don't see that, because male spectrogram has the frequency axis as log scale, as you can see here, 512, 1, 10, 24, 2048. So you will see those equally spaced range of harmonics, because that's basically now everything is log scale. At the top, it's not that, frequency, because now it's in log scale, not in real, um, linear scale. Yeah. So male spectrogram is, much more concise and actually capture more the human hearing range. So in this case, anyway, 64 by 64. Imagine if you are using spectrogram, then there's no way you can classify anything. But male spectrogram will allow you to use 64 by 64. And I've also done something about, generating these sounds like spectrogram in 64 by 64 male spectrogram. And then you can train another model to go from male spectrum back to audio, and it works fairly well. So, 64 by 64 male spectrogram is already good enough for a lot of case. In this case, this is what it sounds like. I don't know if it will. Anyway, the same organ sounds. And in this case, you want to train this CNN model so that it generate predict it as organ. And this is the Ensign data set. I can play it out actually. We have the guitar sound. This is the bass sound. So, that's the bank of the sound. This is electronic guitar. Electronic organ. So this is like the ASDR is different because previous ones are like percussive sounds. So when you hold the key, it doesn't hold. But for organ, it's like you hold it, it will just stay there. The last one will be keyboard. Yeah, so this one also holds because this data set is like you hold it for 3 seconds and then you release it. So you can see from the guitar and bass at 3, there is like a clear ASDR. So the release things will be at 3 seconds. Yeah, so, even looking at the spectrogram, like the organ one is so iconic where, it just keep the same energy over time when you have the SD part where you just keep that energy. So, you can definitely just by looking at this spectrogram, you see some of the correlation between what instrument would that be. So this is like a huge data set. It's like 300K-ish. And it's actually produced from 1,000 commercial sample libraries for all 11 different instruments. And it has like different MIDI pitch from 21 to 108 if that sample libraries actually have those, and press in 5 different velocities, 25, 50, 75, 100, and 127. So that's like the linear, sort of like linearly span interval of MIDI velocity. But basically, I've also done the pre-processing. So it's like now it's like a train.zip and validation.zip and then test.zip. So it would be here. I will talk about it more on Wednesday, but this is what PA4 would look like. Yeah, so not yet ready yet, but you can find the data set here. It's just a trend.zip, valid.zip, test.zip, and there's also example files, but you will download these files to train your CNN models and you will test it on the test set. And yeah. So likely you can do it in Google Colab. The training should be 1 to 2 hours. So you have to wait, but it shouldn't be too tricky to train it on Google Colab. The downside of Google Colab is it will clear everything every time you do it. So once you train it, definitely save your train model in your Google Drive. So there's a way you can mount your Google Drive onto Google Colab. So I will go through, in this Jupyter Lab where you can basically do this drive dot mount content drive. So you can actually mount your Google Drive onto Google Colab. So now you can also save something to that. So when you save the model, you want to save the best model or the model over time on the drive rather than on Google Colab where it will got erased. So once you've done that, then once you train it, you can save it in your Google Drive. Then later you can do the analysis separately. Yeah. Um, cool. That's it.